There we go. So I call this workshop, How Does Your Code Really Work? Because I think it talks about how, everything is really stored on the lower level and how things are working in like the circuitry level. So I'm going to start off with something that seems maybe a little bit unrelated, but I promise that it'll kind of circle back around. So what is computer science? I'm going to give a definition of computer science as some way to turn an input into an output. And this input to an output will go through this black box. And this black box is what you as a computer scientist have to compute. So whenever like maybe I'm making a program where you're going to input a number and then you're going to have to output the double, the black box would be what I as a programmer have to implement. Or maybe I'm doing something way more complicated, like maybe I'm doing this mouse function, and I'm having an input of my keyboard being of my trackpad being pressed down and then me moving it around, and I have to turn that into all these pixels on the screen. Or you can have an even more abstract approach to it, to like my job as a programmer is to take in questions from my boss, and then I have to take in like instructions from my boss, and then I have to compute what they want, and then turn that to output. But basically, what I'm trying to convey is that almost every single thing in computer science can be conveyed as an input to output, and you as a computer scientist have to create the system that will convert the input into the output. So how do you do this? Um, I the way that computers actually represent the input and the output is in something called binary. Do you know what binary is? Oh, great. I'm going to go over how binary is counting, and then I'm going to go over how binary can be used to represent other forms of information. So binary is it's a number system that uses zeros and ones, but then in computer science, you can use that as on and off electrical signals. Oh my God. On and off electrical signals, which will then represent the same thing. So let's just start with counting. 000. What number do you think this is? I know if you know binary, it might be a bit trivial, but yeah, great, it's 0. How about this number? Yeah, 1. So the first two digits are completely fine. They're exactly the same as in our regular counting system. Do you know how you would represent 2 in binary? Yeah, exactly. So because in binary you're only using the digits of 0 and 1, you step through your first, oops, that's not what I want to do. You step through your first combination of 0 and 1 in the ones place, and then after you ran out of digits, you say, oh, well, I don't have any more digits to increment in my ones place. Let's just increment 1 in my tens place, which in binary is the twos place, but it looks like the tens place. The tens place over here, and then let's reset our ones digit to 0. So because we ran out of digits to increment in our ones place, then we're going to increment 1 in our tens place and then reset our ones place. So that's how you count in binary. This is the second possible combination of numbers. And then I'm just going to flip through it because I think that you already know this. So that's 10. This is 11 because then you're incrementing the one place again. And then you go to 100 because you can no longer increment the tens place or the ones place. So now that you've exhausted all of those digits, then you can increment your next value. So that's about what it for counting in binary, and then you can start all over again. So a quick way to convert from binary to decimal, which I won't go into too much, but in every single counting system, the value of a place is the base that you're counting to the power of that base. So what I mean by that is that in base 10, your ones place is a ones place, which is 10 to the 0th. And then your tens place is your 10 to the power of 1 place. So every single digit in your tens place is worth this amount times 10 to the power of 1. Now over here, you have 4, and 4 is every single one of these well, the number of 4 is not just 4, it's actually 4 times 10 to the fourth, because this is the place, which is 4 into the number, if that makes sense. Well, it's 5 into the number. If you're Yes, it's 5 into the number. So since this is the fifth digit place, then it will be represented as 10 to the fourth. So that is 4 times 10 to the fourth will be the value of this number in the entire value of the entire number. I'm just going to very quickly re-explain that because that was not a fantastic explanation. But this 2 will be actually equal to 2 times 10 to the power of 0. And then the 7 in like when you're trying to compute the entire value would just be 7 times 10 to the power of 1. So this would be 70 plus 2 for the first 2 digits, which would then be 72. So in binary, it does something very similar, except now you're counting in base 2 instead of in base 10. So with base 10, after you get through every single digit in your ones place, then that's saying like, oh, hey, I just ran through 10 possible digits. So let me increase my tens place by 1, because now I'm out of all my 10 possible digits. In the base 2 system, once you've run through all of your possible combinations, all of your possible digits in your ones place, then now you're going to add 1 to your twos place, because there's only 2 digits. So it's like, hey, I just exhausted 2 digits. Can you keep track of the fact that I exhausted 2 digits, which is then going to put a 1 in the twos place. So a more mathematical definition of that is that every single place value is equal the value of the digit at every single place value. So like the value of this 1 in the entire number is equal to 1, or the digit at that place value, times the place value 2 to the power of the place value minus 1, technically, because it's accounting for it starting at 0. So if you understood that whatsoever, do you know what the bottom so every single one of the values of these digits would have to be added up to create your final representation in base 10. So do you know what the value of this number on the bottom would be? It was not a fantastic explanation, but yeah, exactly. It's 25. So over here, this is 1 times 2 to the fourth, which is 16, plus 8, which is 24, plus the 1 over here. So yeah, it's 25. So how do we represent other types of information? So we just talked about how you count whole numbers, which is great. You know, you use whole numbers all the times in computers, but there's other types of information which are prevalent in computer science, and it's important for us to be able to represent them. So I'm going to talk about floats, then booleans, and characters, and strings. But starting with floats, actually, not starting with floats. There are limits to how much information you can store in a computer, basically. So since there's a limit to how much information you can store on a computer, humans have said that a number can only be a certain size, because if I used infinite digits, then I would run out of all the space on my computer. So I want to restrain that to a set amount of size. So what that basically means is that we only use a certain amount of bits for our data, and a bit is a binary digit. So when I'm computing and I'm storing an integer, I'm going to call that a 32-bit integer, because it is only 32 bits or 32 digits long. So because of restrictions on how much size there is how much space there is in your computer, you can only store values of things like integers in 32 bits. And there's ways to circumvent this, but the standard for what an integer is a 32-bit integer. So just for a visualization, to make this maybe a bit more clear, but this is the value of 0 as an integer in Java, or in most programming languages which use 32 bits. And then this is the value of the maximum value of an integer in those languages. So because your computer will only allow you to store an integer in 32 bits of information, then you can't really go past this point on the bottom over here. And this is actually only 31 bits of information because the first digit is reserved for the sign of the number. So if this was a 1, then it would be a negative number. But the top number here is all 0, so it's 0. And then the bottom here is the maximum possible value, which is positive number denoted by 0, and then all 1s, which is around like 2,140,000, I think like 7 something million 000,000. It's not actually zeros, I just forget the exact number, but it's around 2 billion. And past that point, then you can't really use an integer to represent that data. You'd have to look into other data types that your programming language might provide, like maybe a long. But the key takeaway is that there's a limit for how much information or how many bits of information that you can use to store a number. And just to clarify, a bit is just 1 digit. So just a bit more on how integers are actually stored. It's all of these values with the regular counting system that we had before. And then the first digit is a 0 if the number is positive, and then it's a 1 if the number is negative. Just a small aside, if the number is negative, then it will actually flip all of the other bits in the number for the actual representation. So what I mean by that is that if I have a 4-bit number where my first bit is the sign, if it's negative, and then I have negative 1, 1, 1, the result will be it's negative the number if I flip all the other digits and then I subtract 1. So it's negative 1, 1, 1 flipped, which is 0, 0, 0 minus 1. So it would be negative 1. Does that make sense? That's just an aside. That doesn't really matter too much. Yeah, so that's something that it doesn't matter too much. It's just a detail of how computers work. It lets you do some cool things later on, but I won't go too much into it. So that's integers, what we just did. Now I'm going to talk about floats. So a float is a decimal number. It's called a float because it's a floating point number, because like the dot in it is a floating point. But anyways, a decimal is stored as in 2 parts, which is an exponent and a fraction. So it's stored in scientific notation in base 2, which means that if you've ever seen scientific notation before, it's representing a number by a number from 1 to 10, not including 10. So like 1 to 99.999 times 10 to some value to the exponent. So if I have a number like 99, how would I represent that in scientific notation? I should go into what it is a bit more, but scientific notation is saying that you can represent. Oh yeah, exactly. I think that you got it perfectly. I think I should do a little bit of a better explanation if people are watching at home. But yeah, so you said that 99 is equal to 9.9 times 10 to the second. Oh yeah, 10 to the first. I did not catch that, but yeah. So 10 to the first. So that's because 99 can be represented by this number, which is in the range of 1 to 10, times 10 to the first power. So it's just a way of you having a smaller number from a range of 1 to 10, and then you can say how big it is with an exponent. So with how floats are stored in your computer, they're stored very similarly, but instead of in base 10, they're actually stored in base 2. So a float in a computer is stored by having your fraction, which is this bit over here, which is going to be representing a value from, I believe it's 0 to 1, not including 1. So the most this could be would be like 0.999999 something. Times 2 to the something power. So 2 to the exponent power. So in your computer, a float would be stored as this fraction over here, which is going to be a binary representation of a fractional number. And then that will be multiplied by 2 to the power of whatever this exponent over here is, which is also going to be counted. Some details is that this fraction is represented by having each of these values be kind of like the normal decimal system. After you go from, like, the one place is 10 to the 0, and then the 10th place is 10 to the -1. All of these digits are 2 to the -1 here, 2 to the -2, blah, 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 2 to the -23. So it has a fraction that it's going to store in base 2, then multiplied by 2 to the power of this exponent, and then this is the sign over here. Did that make sense? And then there's some other details in there, like I'm pretty sure this is like flipped as well. But, yeah, oh great. So that's how a float is stored in your computer. And just something to point out here is that your float only has a certain amount of digits to store the actual fraction of your number. If you have a number that's really precise, like let's say that you're trying to store pi, then obviously, well, maybe not obviously, but because pi is infinite digits, then you wouldn't be able to express that amount of digits in this fraction over here. So your floats can only be so precise. They can't really store that many significant digits. I know that this says 23 over here. I'm pretty sure that a double, which is a float, which is 64-bit, so it's a bit bigger than this, can only store up to like 15 significant digits. So it can only have like a 15-digit number in base 10 that is stored correctly. So that's important to know. So a Boolean in computing is just known as a bit being on or off. So a bit being on will make it true, and then a bit being off will make it false. So I didn't actually say what on and off are, but a bit being 1 will be representative of the value of true, and then a bit being 0 is false. So I could check like, hey, is this value true or not? And then I can say, oh, that bit is a 1, yes, it is true, or oh, that bit is a 0, it's not true. I think that's hopefully the most self-explanatory bit of it. So then now we're going to go to characters. So characters represented in binary are a bit different from everything else. So characters were represented in back when this first came out, which was I think like probably the 50s or the 60s, in something called ASCII. And what ASCII really is that it's just a lookup table. So it's just a lookup table from numbers, which we already know how to represent in binary, to characters. So if I had 65, what would be the value of 65 as a character with this lookup table over here? And this column over here, the decimal, is the decimal value. Yeah, exactly. 65 would be capital A, because it would just go to this table and say, oh, hey, 65 is capital A. So fantastic. Over here, a basic explanation of computer memory before I get into strings is that computer memory is basically, it's a grid. I'm going to talk about more about how this works later, but a computer memory is organized in a grid where you just have all of these boxes, all of these memory cells, and each of them have a memory address. So this one might be my first address, this one might be my second address, which is going to be address 0 and address 1. This would be address 2, 3, 4, 5, 6, 7, blah, 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 blah. And then if I want to store a value, then that value would be stored inside of one of my memory locations. So my memory is really just a big grid, and I can say, hey, at column, 1, row, column 1, row, okay, row 1, column 4, I'm going to store the value of 72. And then the columns and rows will be is your memory location, and it will, well, the columns and rows will correspond to your memory location, and it will be able to find that row that you're looking for. Does that make sense? Oh, great. Yeah, so computer memory is just, it's in a big grid. And over here, you might notice that this value exceeds the limit of one box? That's because each of these boxes can only store 8 bits of information, or 1 byte. It's just known as a programmer term that 8 bits is 1 byte. I think you probably already knew that, but in case other people were watching it later. But anyways, um, since a since in computer memory you can only store 8 bits per every single box, then usually if you have a number that's over 8 bits, or over 1 byte, then you can just store it by like splitting up the value into the next 4 cells. So you can say, hey, 2 billion is gonna be, yeah, 2 billion as my integer has to go across 4 different cells. Let me just say that it starts at index at this location over here. And then I'm just going to I'm going to store the value of 2 billion, or whatever this number is called, as this cell. But then whenever I access this number, I'm just going to remember that, hey, I have to access all of these other values as well. So basically, you just put the, if you have a value that's over 1 byte, then it'll just overflow. I shouldn't say that word, but it will just go on to the next cells, and it will just put all of the information one piece after another, and then it will put the first bit as the location, the first memory address of your value as the location of that number. Did that make any sense? Oh, great. So on to why this is at all useful. Let's just, with a string, a string is very simply just a bunch of characters, one after another in memory. So over here, I will have the characters of 72, 73, and 33, which is high with an exclamation mark at the end. That is just this. It differs a little bit depending on which programming system you're using, but almost every single representation of a string will have this component at the very least. So it'll have every single part of the string, just every single character of the string, just one after another, and it'll say, hey, if I want to remember where the location of the string is and maybe store it in a variable, then I'm going to say that the location of the first character in my string is going to be the location of my string, and then I can just remember where I can just remember how long the string is, and then I'll have every single character in my string that I know the location of. So just for a more visual representation, if I have this over here, which is my string, I'm going to store it as remembering the location of the string, and then I'm going to remember the length of the string. And then this string, which is just all of these characters one after another, I'm going to say, hey, I can just get you by saying OX3, which is the location 3. And then I'm going to remember that the length is 3. So then if I want to get if I want to like print out my string, then I would just print out every single character at every single memory location. I would print out 3 characters, one after another, at the beginning at the start of my memory location. So I'll just say, okay, OX3 is the start of my string, and then I'm going to, since it's 3 characters long, I'll print out the character of H, and then the second one and the third one. Does that make sense? Great. So just a clarification, this is how it's done in Java. There's like some other languages do it differently. I know that in C, you actually don't have a length, and then you have a special character at the end, which is called it's the null character. So you would say, okay, start at OX3, and this would be my string, and then just keep on going until you hit this null character. So just to point out that it differs by which programming language that you're using, how the string is actually implemented, but it will almost always, I've never seen it not have this system over here where all of the characters are just one after another, and it remembers where the first character is. So that's how almost every single type of data in your program is stored. Now, how is it actually stored? So I've said, oh, it's all these zeros and ones, and you have these memory locations. But on a circuitry level, like you can't just have a zero and have your computer say, oh, okay, that's a zero. You have to have some way of converting these zeros and ones into actual logic that your computer can follow with electric circuitry. So I'm going to start off with transistors. So transistors are basically just an electronic switch that will control the flow of electricity. So over here is my example. And there's an input wire over here, there's two. And then there's an output wire over here. And if you, the base is, I don't actually think it's called the base, but I think, ignore that. If you put electricity into this transistor, which is signified here, then it will allow the flow of electricity to flow. So I'm going to show this in a better representation. First of all, I love transistors. They're the building block of every single fundamental piece of computing ever. But I'm going to show it like this. So if I have a battery and both of my transistors are off, when I have a transistor that's off, it will be blocking the flow of electricity of the wire that it's attached to. So if I were to turn the first transistor on, then it will allow the electricity to flow through the first transistor, but then it will be caught at the second transistor. What would happen if I turn the first transistor off, but then I turn the second transistor on? Yeah, exactly. So since a transistor will block the flow of electricity if it isn't given electricity, if the first transistor is on, then if the first transistor is off, then the flow of electricity will be blocked. But even if the second transistor is on, there's no electricity over here, so it's not able to let anything through. So how would I be able to light up the light bulb in this diagram? Yeah, exactly. So if I turn both transistors on, then hey, electricity goes through, and then now I have a light bulb that is turned on. So maybe you don't know this, but maybe you do, but you have just created an AND gate. So a AND gate is really just a wire with electricity, and it has two transistors as input, and then your output is if the wire is still on. So I have a wire like a battery over here, and then I am requiring both of my transistors to be on in order to turn on the light bulb. So I didn't actually explain what a logic gate is, so let me go over there. So a logic gate is really just a circuit that will take in two binary inputs and will output one binary output. So an AND gate will take in as input two binary digits, and then it will output another binary digit based off of what those two digits are. It's like a way of combining two binary digits in a way that will hopefully make sense for you in your later applications. But it's like it's an operator on two binary digits. So the AND gate is a way for you to put in two binary digits, and then you will only return a one or an on if both of your binary digits were 1, and then it will return a 0 if either of your binary digits are off. So what that means is that over here, your AND gate is really just saying, hey, take in two transistors and then connect them to a live wire, and then say, hey, just measure the output of these two transistors, and then that output will be the output of your AND gate, and the inputs will be the electricity that you put into the two transistors. Does that make sense? Oh, great. So I'm gonna do something over here called abstraction. So I don't have a slide for it, but abstraction is the process of taking away the lower level details and then just working with some easier to understand, more complicated things like an AND gate. And I'm gonna say that, hey, I know how to make an AND gate. I don't really have to just I don't have to draw this. I mean, it's not that complicated, but more complicated than just an AND gate. I don't have to draw this pretty complicated diagram every single time that I want to create an AND gate. I'm going to abstract away the details and just say, okay, an AND gate is a gate that looks like this. It's a little, like a, like a, I don't actually know what shape that is. It's like a house with really round edges. And it will take in two inputs and it will output a one output depending on, it will take in two binary inputs and it will only output a one if both of the inputs were one. So I'm going to abstract away the details of what the transistors are doing and just replace them with saying, hey, this is an AND gate. It will, it has the ability to take in two binary digits and then output one binary output. And another thing I'm going to do is I'm going to say that, hey, I know how to make an AND gate. I'm just going to say that I know how to make all of these gates. I know how to manipulate these binary digits now. So I can make an OR gate, which is another gate where it will take in two binary digits and it will only output one. It will output one if either of the digits are on, and it will only output zero if neither of the binary digits that are input are, if they're both zero, it will output zero. And then I'm going to abstract away all the details and just say, hey, I know how to make an AND gate. So I have the logic and the understanding of how all these other gates are formed. So an OR gate is something that will take in two binary values and it will output one if either the first binary input or the second binary input are one. So if either of them are one, then it's going to say, hey, okay, that's great. I'm going to output a one. So that'll be on if like one of them is on. And then an XOR gate is a different gate, which I'll use, which is saying that if either of my inputs are the same, then I'm not going to output a one, I'm going to output a zero. I'm going to be off. If my inputs are different, then I'm going to output a one. So this XOR gate will take in these two digits over here. And if the XOR takes in a zero and a one, then it'll output a one. Or one and a zero, it'll output a one. But if the XOR gate takes in two zeros or two ones, then it will say that's the same thing. I'm not going to output a one. Does that make sense? Okay. So yeah. So I'm going to be abstracting away the details of what the transistors are actually doing on the lower level. And I'm just going to be saying, okay, these are some gates. They'll take an input and then they'll output a value. So I'm going to go on to how are logic gates actually able to run computers. So I've made these logic gates, but like, why am I making the logic gates? How do they actually help me run my computer? So I'm going to make an example where I'm going to be adding two numbers with logic gates. So 0 plus 0 is 0. I'm not going to bother you with the trivial math of like 0 plus 0. 0 plus 1 is 1. 1 plus 0 is 0. In binary, what is 1 plus 1? I don't think that's actually that necessary that I say what 1 plus 1 is. Well, that I ask you what 1 plus 1 is. So I'm going to say that in binary, 1 plus 1 is 1, 0, because that would be the equivalent of 2 in binary. So how can you represent this in binary? Well, with logic gates. So you can reconstruct this addition as a table. So I can say I'm adding one number as input and I'm adding another number as input, and I want to get a carry and a sum. So the carry is my twos place or my tens place, and it's the value that gets carried over if the sum is full, and then the sum is going to be the ones place. So do you know what logic gates I can use to represent the carry and the sum of my addition? If you remember from the previous slide a couple of those. like, do you know which logic gate could be used to represent this truth table over here, where I'm taking in my two inputs and I will output a carry if both of them are on? If you don't know them, that's okay. I will answer. But I should ask first if you have any questions, because I feel like I've sped through a bit of the material. So do you have any questions of which you might want to ask of me? Okay. So the carry okay, that's fine. Yeah, that's fine. So the carry is just an AND gate. Um, that is something I did not spend a lot of time on. And then the sum is an XOR gate. So over here, I'm just going to represent my addition as two logic gates. So I'm going to take in my two digits to add my A and my B, and I'm going to just pass them through these two gates, and then my output will be the sum and the carry. So basically, I can just pass in my numbers through some logic gates, and I can get the sum and the carry of adding two digits together. Now, this is great, but with regular addition, there is an issue. So I'm going to go over that now. Whenever I'm adding two numbers, if I have a carry, like let's say there's one over here, and I try and add it to my next two digits, then hey, I'm not adding two digits anymore. I'm adding two digits plus the carry over here. I'm adding three digits. And adding three digits is not something that our program can do right now. Now it has to compute a one, but we don't know that it can do that yet. So we have to modify our original adder in some way. So right over here, we have a half adder. And that's the logic gates that I used before. But I'm going to abstract this again. I'm going to abstract the details of how I'm implementing it. And I'm going to say that a half adder is something that will take in an input one and an input two, and it will turn that into a carry and a sum, which is just adding it. The carry will be the tens place and the sums will be the ones place of an addition of those two numbers. So a full adder is something else which will take in three inputs. That should say input three. Take in three inputs, and it will output a carry and a sum based off of what those inputs are. How would I make a full adder something that adds together three digits with a half adder, something that adds together two digits, like intuitively? How can I add together three numbers by using a system that adds together two numbers? And you can use it multiple times. It is a very difficult question. But... No, that's fine. So you can create a full adder by adding together two numbers, and then you can add their sum with another half adder. So you can add together three numbers by adding together two of them, and then basically adding together their result with another half adder. But then you have to do something else with the carries, where you basically make sure that if either of them are in the tens place, then you output a carry. But what this basically does is that I've abstracted what a half adder is, where I take in two inputs and then it will output a carry and a sum. And I've turned that into this over here, which will use that, and it will take in two inputs. It will pass them through the half adder, and then through the half adder, it will add those two digits together. Then it will add together the result with the third digit that you're using, and then it will compute your carry and your sum. So just to go through an example of this, if I have 1, 0, and 1, then the 1 and the 0 will go through the half adder. The tens digits will be 0, the ones digits will be 1, then the 1 and the 1 will go through the half adder. The tens digit will be 1, and the ones digit will be 0. And then 0 and 1 or together will give you a 1 and a 0. And that's correct. 1 plus 0 plus 1 is 1, 0. That makes sense? Do you have any questions? This is hopefully the most complicated thing that is in the demonstration. Kind of. Okay, great. Yeah, so it's less of like a do you understand this completely, but it's more of a do you understand that you can use logic gates to compute stuff and to combine digits in a way where you can compute values from those digits. So did that message get across? Oh, great. So yeah, this isn't like I expect you to like become a master of logic gate addition, but I'm really glad if you got that out of it. So I'm gonna abstract a full adder as well. I'm gonna get rid of all those details and just say a full adder is something that will take in an input, 3 inputs, and will output a carry and a sum based off of what those are. And then I'm going to make an 8-bit ripple carry adder, which is from Crash Course. I took the visuals from Crash Course. Well, I made the ones on Google Sheets. I took these from Crash Course. And a 8-bit ripple carry adder will take in your first 2 digits, pass them through a half adder, then take the carry of that half adder and then pass it into a full adder. Then take the carry of the full adder and then pass it into another full adder with the other digits. So in order to actually visualize this, I'm just going to do addition with a 4-bit version where I have, let's say 1, 0, 1, 0, and I'm going to add that to 0, let's say 0, 1, I want to make it 4 bits, but 0, 0, 1, 1 plus 0, 0, 1, 1. So my first 2 bits, I'm going to put through a half adder. And a half adder, when you put 1 plus 1 through it, it will give you a 0 as your sum, and then a 1 as the carry. When I pass 3 ones through my full adder, it will give me a 1 in my sum and then a 1 in my carry. Then I'll pass in 3 of these 3 digits through my full adder. So over here, I'd be on this step. And then that will give me a 1. And then I'll take my carry of 0. And then I'll put my 0 and I'll put my 0 and my 2 digits over here into my other full adder, which will then give me an output of 0. So does it make sense how I just added together these 2 binary numbers with my logic gates? Oh, great. I'm not okay. Oh, actually, that was from the earlier. That was from the earlier response. You don't really need to be like too clear on this one, but oh yeah, it is really confusing. I think there are videos for this where like it's like probably like 2 hours for this and a bit more. So I condensed it a lot, which might make it a bit too confusing. But hopefully, yeah, if you get a general idea, then I think that's great. You're passing your bits through adders, and then you're eventually getting your final sum at the right. So now I have the ability to add together 2 numbers. So I'm just gonna very basically go over memory storage with logic gates. This will feel incredibly like vague and a bit rushed. But I have memory storage with logic gates, and I'm just gonna introduce this thing over here, which is a way of storing memory permanently. So if this bit is 0, what will be the output of this OR gate? If an OR gate will take in 2 digits and it will only output 1 if both of them are 0. And say that like this is initialized to 0. Yeah, it will output 0. So now let's say that I flick this on for 1 second to be 1, and then I turn it back to 0. What will be the output of this logic gate now? Yeah. So After I flick it on for just 1 second, then this output becomes 1. And then that 1 cycles back into the OR gate. So now it will permanently be 1 because all an OR gate needs to be 1 is to have one of its inputs be a 1. So this is a way of like an easy example of what permanent memory storage looks like. Not permanent, but a way for you to like flip on this switch and then have the bit inside of your OR gate be permanently on. So I will not go over what this is in too much depth, but this is something called an AND OR. This is a basic AND OR latch. And yeah, this is an AND OR latch. So what this means is that if you flick the set on, so just for like 1 millisecond, if you're saying, okay, turn this on and then turn this off, then the output will be 1. And that is because the, I believe, yes, it's because this comes back into here. So once it's 1 for a tiny bit, then it will, once the output is 1 for a tiny bit, then it will cycle back around. And then if you want to reset it or flip the output to 0, then you just flip this on for 1 second and then you flip it off again. And then that will make it so that this output wire is 0, and then the 0 will cycle back around, and then your OR gate will be off again. So basically, what this is on a high level is a way for you to flick on a bit. So it allows you to flick on the output. So I can just turn on the set to 1 for like a millisecond, and then the output will permanently be 1. Or I can flick on the reset for 1 millisecond, and then the output will permanently be 1. Does that make sense? Great. So now I'm going to show you the most terrifying visual of the entire presentation, but this is how memory is actually stored. So if you remember earlier when I said that memory is in like a big grid, this is that big grid, but just a little bit more, it just shows a little bit more detail of how it's constructed. So every single column of your grid has a number, and every single row of your grid has a number. And then if I want to access the bit, let's say over here, then I would be accessing the bit at column 0, row 1. And if I want to change this value, this over here is a little bit more, it's a more complicated version of what I showed last slide. So it's a way for you to, it's a storage location. And then if I turn on this wire and this wire, then I can index into that bit, and then I can turn it on or I can turn it off just by flicking it on or flicking it off. And then after I flick it on or off, then I can leave it there. I can stop transmitting electricity through those wires, and then I can move to like another bit and then do the same thing. So basically, this is a bunch of permanent memory, not permanent, but long-term memory, where I can index into it, and then I can flick on the bits. Does that make sense? Oh, great. So just a small detail is that a memory location, if you've ever seen OX something, OX is the way to say hexadecimal, which is another base system, which I won't go into, but like how binary is in base 2, which only uses zeros and ones, hexadecimal is on the other end of the spectrum where it uses more digits than 10. It uses 16 digits. So as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then instead of stopping there, it goes A, B, C, D, E, F. So it's just a way for you to represent numbers in a more compact space. But if you have a memory address in hexadecimal, then the first half of your memory address will be your column, and your second half will be your row. It might be inverted. But let's say that I have a memory address where the first half is 0, 0, and the second half is 0, 0. Then this half would be the row, this half would be the column, and this half would be the row. So my memory address over here would be 0, 0, 0, 0. And then if I wanted to go to the next column, then this would be 0, 1, 0, 0. And then if I want, yeah, because that would be the next column because I'm changing this to a 1. And then I'm saying go to this column and then that row. Does that make sense? That's not the most like clear explanation. Oh, fantastic. So that's the basics of what memory addresses are. And this is how your computer actually stores these binary values from earlier. And there's also a way that your computer can get these values, and then it can say, okay, like transmit this value out, get the value at this bit, and then store it somewhere else, so that you can use it for stuff like addition earlier. And then that was how a single bit is stored. If you want to know how the grid from earlier, where every single cell is a byte, is stored, it's just 8 of these, and each one of these things over here, I think it's called like a multidexer or something. Like I forget the actual name. It's got some really cool name. Anyways, each of these grids will be responsible for one of the bits of my 8-bit number. So of my 8-bit value. So over before, when I had 72, 73, 74, maybe like one of these values, maybe location OX0000, for the memory location OX00 on all of these grids would hold one of the bytes for my 72. Then OX0100 would hold this would be like 72 would be my first value. And then that would be constructed by taking a bit from every single one of these grids. And then 73 would be constructed by taking the next bit at the next location for every single one of these grids. Does that make sense? So because a byte is 8 bits, then this is the 8 bits that make up that byte to store your values in your memory. Yeah, I mean, it's not the simplest thing, so I think it's fine if you're a little bit confused, but I think that's mainly what I want to say, that memory, that your logic gates can do this stuff where it's like indexing into all of these locations. The details of it mostly don't matter, but if you got most of it, I'm going to say that that's hopefully enough. So on a higher level of abstraction, logic gates can add two numbers and store values permanently. So I'm going to make a really bold claim. I'm going to say that I'm going to abstract away all logic gates and say that logic gates can do anything with binary digits because they have computation and they have permanent memory storage. I'm just going to say they can do literally anything. So maybe that's not like the most simple, maybe that's not the best like line of reasoning. I think that if I said that to like a teacher and I was like, I bet this is correct, I think that they would not give me credit. They would say, you have to prove that a bit more robustly. But I'm just going to say it here because it's how it does work like that. They do everything on your computer. So the one final thing that I'm going to talk about is on the highest level of abstraction with logic gates, is that they make up your CPU, and your CPU, your central processing unit, will take in binary instruction code and memory addresses. So let's say that the code in binary for addition is 0100. And then I can pass in two memory addresses after that. So maybe like OX0000 and OX0100. This will add these two numbers together, and then the number in this location and that location. And this is saying the operation that I want to do is addition. So I'm saying that I'm going to pass in three values. I'm going to say, here's my instruction code, addition. I'm going to just say that this is addition. And then I'm going to pass in the values of the location of the first number I want to add and the second number I want to add. And then my computer with all the logic gates will run this and say, okay, let me get all the bits from this location, add them together, and then let me store that in, I'm just going to say it's going to store it in the second address. So let me store the addition of these two in the second address. Does that make sense? And by the way, the operation codes are like an arbitrary lookup, like a ASCII chart. It's saying, hey, like, 0100 is addition. And great. So this is the most primitive way of coding. It's one step down from assembly. So assembly is literally just this, except instead of 0100, this would be like add. Oops, that's a bit too tall. Add. And then you'd have a compiler which would take in add and then it would turn it to 0, 1, 0, 0. And then maybe these memory locations would be in like hexadecimal instead of binary. But anyways, going over to the CPU, the CPU will this is maybe a bit more complicated than it needs to be, but your instructions will just be at some point in your memory. I'm pretty sure it usually is the very top of your memory. Your CPU will read in these instructions, which are stored at the top of your memory. So in the charts from earlier, like over here, the instructions would be in memory location 0, and then the next one will be in memory location like 1 and whatnot. But all of the instructions will be one after another in my memory, and then my CPU will just read those instructions one after another, and it will execute the commands in those instructions. So the instructions are stored in the same place that all my data is. So it would run instruction 0, instruction 1, instruction 2, and then it would continue running. Eventually, there's like a stop running instructions command, which would then stop running the instructions. And then eventually, after some time, there's some data down here, which would then also be accessed, which would be accessed by the commands that you're running. Does that make sense? So what I'm trying to say here is that your computer will just run all these instructions one after another, and it can access memory that's also, the instructions are in your memory, is what I'm trying to say, and it will run them all one after another. Great. So that's basically the workshop. We just went over how almost every single computer on the planet works. Transistors are used to make logic gates. Data is represented in binary. Primitive code is executed on your computer, which is used by the logic gates. And the logic gates use these binary representations of all your data to do all these cool operations. So I'm sure you already know this, but what can all of these tiny pieces of electricity and logic gates really do? So I'm just going to show a video that I think is cool. It's of the MIT Cheetah from like 2011. I hope I'm allowed to show this. Oh, that's because it's from my school account. I hope I'm allowed to show this. If I'm not, that will be a little bit sad. But let me just see. I will open it up in another window and I'll just go over there. So I'm sure you know how very cool all of computing is and the potential of it, but I'm just going to show this anyway because I think it's a really cool video. So over here is Cheetahs, an autonomous cheetah by MIT that will. I'm not going to be sharing the video, the sound, but it detects an obstacle, and then using transistors and logic gates, it manages to sense the obstacle coming towards it with like camera information, which is the camera information is then in binary, and then the logic gates use operations in binary to change the values and then turn it into like how it should be controlling the motors, which is then also in binary, and it makes this really cool cheetah. So the cheetah can then just run around and they can jump over obstacles, and it's exceedingly cool. I wish I had one. But that's about it. I just wanted to go over how like just the amazing potential of what logic gates and transistors alone can really do. So I'm just gonna, I think that's the end of the video. I love the cheetah, it's very cool, but that's about it. So do you have any questions for the workshop? Oh, great. Yeah, I have to say, I'll cut the recording now.